Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. And Fred was talking to me about a statistical question, which is the sort of question we like asking at parties and other places we're trying to impress people.
When we want to stay alone in the corner somewhere.
Yeah.
No, it was actually, there's a question that I was bringing it up to you because one of our listeners or readers brought it up, and they were looking at an article on tolerance intervals. I think it was on tolerance intervals. And the question was, well, what's the difference between a tolerance interval and a confidence interval? And of course, I responded as a statistician, and I got a response back real quick saying, well, that's too technical. I don't understand. So I thought I'd ask you, Chris, because you do amazing animations real quick. Maybe that's a good future webinar, So wave your hands for the podcast and everybody will get it just really clear.
Right.
But I mean, so I think there's actually 3 different statistical intervals in play. In this question, I only talked about 2 of them, but there's a distinct difference between a confidence interval, a tolerance interval, and a prediction interval. Is that right? Or are there more?
Yeah.
I'm sure there's more.
Yeah, I think statisticians make too much about trying to separate these 3 definitions, and I think there's some use, some benefit in terms of having technical definitions that apply to different areas, but in some cases, they can be used interchangeably, and we still produce good products at the end. Mm-hmm. But long story short, let's just say you're manufacturing something, and what's something you manufacture where a characteristic is important, a measurable characteristic. Maybe I use bread when I'm doing my statistical process capability courses, and maybe I think I told you one day that actually there's this metric in bread which I love. It's called chewability.
And they can measure it, right?
You can measure it. Yeah, there's a testing rig that can be it can be used on bread to measure how chewable a bread is, and it combines, how much deformation the bread can go,
and resistance and kinds of weird stuff. Yeah,
how much it springs back and how long it takes before it springs, all those sorts of things. Anyway, so either way, there's a number associated with the quality of bread. It's usually it's measured in terms of newtons, actually, even though it's not a force per se. But either way, so chewability of bread is usually in the order of about 7. And let's just say 6.5 is not chewable enough, and 7.5 is too chewy, too chewable, whatever that might mean.
You pull your dentures off, out.
Right. And so when you're baking bread, the normal distribution does a really good job of describing its chewability, how the different chewability numbers will change from each slice of bread you observe or test.
Well, and that makes sense because there's the different thicknesses of the bread pans it's baked in, the location in the oven, the particular details of the mixture and moisture that's in the dough that you're put in there. It has all these little perturbations that can make it more or less chewable. And that's kind of why normal would work.
Right. And it's and for those, we've talked about this a lot, the normal distribution or the bell curve, it has been proven to model random processes that are themselves a sum of lots of other random processes. So all those things you just talked about, Fred, will sort of add up to influence the chewability of bread. Now I'm hungry, Fred. We might have to stop this podcast because that's
well, I've got two loaves I have to bake after we get done with this, so I'll tell you how it turns out. And I don't think sending it to you will do a disservice, but
right. And so, and let's just say we study our baking process and we realize, what, our bread chewability. It's on average, it's 7, which is exactly where we want it to be, and we might be able to create a bell curve or use a bell curve to model how each loaf of bread varies ever so slightly from 7, and we might be able to say, oh, you know what, with with this bell curve we fit, 95% of the chewability measurements that we take from our bread coming off the line fall between 6.8 and 7.2.
Right. Now that's measuring every single one. So you are getting essentially a population distribution here.
Right. Well, you could also do it from a sample. You could just test every 10th one or what have you.
Mm-hmm.
But it wouldn't change.
You would get a mean. You get a mean and a variance, and you could estimate a normal distribution from that, or describe a normal distribution. Yeah.
Right. Or you could use another distribution that tends to do a better job of fitting. And it's just as you know, there's a myriad of ways you can analyze data and say, you know what, we can see that of the bread that we've just produced, 95% of the bread will have a chewability between 6.8 and 7.2.
Okay.
We probably shouldn't get too wed down on how we get there. Let's just say we get there and we happen to use a bell curve. That's tolerance interval. A tolerance interval applies to a measurable characteristic. And so
of the individual pieces, right?
Yeah.
Right. So you were saying we make 1,000 pieces of bread and we measure some of it, and now we know that 95% of them are between these two values. It's of the individual values.
Yeah, of the actual measurable characteristic of something you're creating.
Okay.
And then obviously you talked about the mean, and so that the mean is the average, the arithmetic average, and perhaps we had to estimate the arithmetic average as part of our process to coming up with what we think the tolerance interval is. And the tolerance interval always has to be combined with a percentage. So the 95% tolerance interval is the interval within which we think 95% of our bread chewability will fall. But let's just say we're now not going to focus on the actual measurable characteristic itself, but instead we're going to focus on a parameter of that random process, and the mean is an example of a parameter. It's essentially a factor on which the random process appears to be governed. And of course, the mean's a very important one when we have a bell curve, because it describes where the middle of the bell curve is.
Right. And then variance would be another one. And
variance,
kurtosis, and what's the
characteristic
other one?
life, skewness.
Yeah, skewness. Yeah. And there's all kinds of things. We take a group of data, whether most often a sample, right? But it could be the whole population measurement. And we say, well, where is it centered at? Where is it located? And we say, well, okay, that's the mean. And that's a calculation from that data. It's not the individual data points themselves. It's a calculation, calculated element from describing that data set.
Right. So the random process is going to be, for all intents and purposes, a function of the mean that you uncover and the standard deviation that you estimate, for at least for the bell curve, that is. But those are parameters, like you said. They're not measurable characteristics. They the mean, like in the same way. What's the average number you roll when you roll a dice? The average number you roll is 3.5. You can't roll a 3.5. But that's the average number you roll when you roll a dice, because it's not a measurable characteristic. It's a parameter. So the mean is a parameter of the random process, which you can't directly measure. And because you can't directly measure it, you can only infer information about it. You can never directly measure it. You can only ever infer information about these parameters, which you observe or you study through literature, for example. And the confidence interval represents your understanding of what that parameter is. So the tolerance is a measure of your product, and the confidence is a measure of you. And the confidence is if we have a confidence interval, 90% confidence interval for our mean being between 6.9 and 7.1, that means that we're 90% confidence the true value of the mean lies between those two boundaries.
Well, does confidence intervals only apply, one, on parameters, but two, when using a sample from a population? Because if we have 100% of the population measured, we there's no uncertainty of where the mean is, because we have all of the measurements, other than measurement error.
Right. And this is where we get into debates between statisticians, because some will argue that you can create confidence intervals based on expert judgment, which involves no samples. And some will say,
aren't we clever?
That's right. But and that's where you, and that's actually a really powerful way of generating confidence intervals, because if you have people who've been around a manufacturing process for a while, a baker who bakes bread and routinely measures chewability, they'll be able to say, oh yeah, there's that one time in 1998 where we tried this flour and it was down on this and more on that, and that increased the chewability this way. That profound corporate knowledge is very valuable. So if you ask a baker, like, what do you think the chewability of this bread's going to be? It's a lot of information in there.
Yeah. So, and they have that amount of knowledge to give you a rational number.
Right.
Value or estimate of what the measurements will be. Yeah. And it comes in handy because if your measurement system, if what measures the chewability is out of whack, somebody with enough experience will go, well, that doesn't seem to be right. Let's check it. Whereas somebody that doesn't know what they're doing, they'll get a number and they'll go, oh, it's 15. With 15 equates to chewing on beef jerky. It's nowhere near what your bread is. And it's like, all right, well, something's not right here.
Right.
But if you don't know, it's a number and you run off with it. That's different than what I think of as a statistical confidence interval, though, because what you said, it's where the true parameter is likely to exist based on the information you have.
Right. And I think, and so some of you might be saying, well, that's just semantics. And to an extent it is. But so the tolerance applies to a measurable characteristic. Tolerance interval applies to the measurable characteristic, and a confidence interval applies to our understanding of a parameter. And some of us might be saying, well, isn't a tolerance interval just a confidence interval on a measurable characteristic? And from one perspective, you're right. But the reason why they're different, technically very different, is because a confidence interval technically applies to a parameter. The fewer samples you have, the wider your confidence interval is. And the wider the confidence interval, the less confidence you have.
There's this square root of n that gets involved in there, and n being the number of samples you have. And so it
depending on the model, yeah, but square root of n is a really good guess about how big your confidence interval gets. So if you have 1 or 2 or 3 data points, your confidence interval is very, very wide. But technically, your tolerance interval won't change if you have smaller samples. It will become more and more accurate when you have more samples and you're able to work out, the range within which those chewability measurements are going to fall. But technically, your tolerance interval won't change, or the width of the tolerance interval won't change if you get more and more samples. The accuracy will be refined, but it won't inherently get wider.
Right. It's not a direct correlation or factor of width to sample size.
Right. And that's one of the biggest differences between confidence and tolerance. In a way, tolerance interval is our best guess at where 95% of those chewability measurements are going to fall within. Whereas confidence is a measure of what is our best guess? What guesses could we have on the parameters which we get the tolerance interval from?
Now, is tolerance intervals, is it related to this? I'm trying to think of the name of is it Chebyshev? Yeah. Well, what's the name of that? There's some law or rule or whatever. I think that this famous Russian statistician, I think he's Russian, Chebyshev, came up with it, but it was independent of any distribution. In like 3/4 of all data points will be has this certain range based on your data. But it's very vague. It's great big wide swaths of ranges.
Right.
Where if you know a little bit about the distribution, then the tolerance intervals are much smaller than what Chebyshev's inequality, I think is what it was called. Is that right?
Yeah, and I don't know how you pronounce his name. I think I've heard it Chebyshev.
Well, it's spelled like 6 different ways too.
Yeah, true. It's not written in the English alphabet. It's uses acrylic language, so there's always something that you lose. As I understand it, Chebyshev's theorem is is mostly useful when the only thing you have is a standard deviation and a mean and nothing else. You don't have.
You don't know it's normal or Weibull or skewed or not skewed
Right.
or bimodal or whatever. And yeah, if you have the mean and standard deviation, then you know with so many samples or you're within so many standard deviation of the mean, it covers 75% of it. I think it was like two standard deviation covers 75. All the data points will be within two standard deviations will be within some value, some range. Right. If I'm saying that right.
Yeah. It's an inequality because it gives you the upper limit on how many data points can be you'd expect to be within a certain range.
Right. But as soon as you say it's normal distribution, then you use the mean and standard deviation directly.
Right. Or if it's a Weibull distribution, you use the scale and shape parameter because you now have more information. And so Chebyshev's inequality is applied to scenarios where the only thing you know is the mean and the standard deviation and not the model. And even then it gives you an upper limit on how many data points you expect to have within a certain range away from the mean.
Right. And one of the other things I run into is that Chebyshev's theorem doesn't apply when you only have a mean. If you don't know the standard deviation, you don't know anything. So once again, it's why I say don't use MTBF. Just don't do it.
Yep. But
so that is related to tolerance, but it's in the case when you really don't know the distribution.
Right. In which case, if it's $1 million decision, find the distribution.
Yeah. So, find the distribution because it's a rough estimate using Chebyshev. It's the upper limit and. Yeah, it's not precise enough for $1 million. It's not precise enough for a $10 decision, in my opinion, but whatever.
It's really useful if for whatever reason you can only ever get the mean standard deviation, but there's precious few scenarios where that is a limit.
Yeah. Well, you haven't talked to the vendors I've been talking to.
I mean, don't. I'm excluding the shortcomings of the human ego.
There you go. All right. So one of the other ones I mentioned at the top was that there's a prediction interval. What's that about? Because I just draw a complete blank on it. I know I studied it. That was one of those learn it enough and then dumped it because I've never used it.
That's a third one. And so that's the third one. The prediction interval is essentially what's going to happen in the future. And so the tolerance interval technically applies to a population that you've studied. So if that bread scenario, you might be measuring every 10th loaf of bread. You can't measure every loaf of bread because
it takes time and money and resources and it's destructive.
When you test for right, yeah, if you have to take a slice of bread, put it on a machine, and as a rule, customers frown upon having this now mangled slice of bread shoved back in its loaf and being sold at the same price.
Well, I could see in a bakery, you would do all your testing just before breakfast or lunch or something like that. So now you have all this bread ready for toasting. That's just, thinking yield and I'm sorry.
That's all right.
Yeah.
But so the prediction interval is what's going to happen in the future. And now people become, again, this is where semantics can sometimes get in the way, because if you know the tolerance interval for today's loaves of bread, shouldn't that then give you some idea of what's going to happen tomorrow? And the answer is absolutely yes. So the tolerance interval can often be reasonably concluded to be what's going to happen tomorrow, if that makes sense.
And that's on the individual measurements that we make in the chewability.
Right. But prediction interval can also allow for a lack of confidence in the parameters. So if your best guess at the mean and the best guess at the standard deviation means that the tolerance interval is this, then for prediction intervals, there are mathematical and statistical things you can do to take into consideration. Well, that might be based on your best guess of mean and standard deviation, but here you've given us confidence intervals on those two values, so the prediction interval will be a little bit wider because we're going to take that into consideration. But prediction interval is used a lot in both frequentist statistics and Bayesian statistics. And then there's all sorts of other things like the credible interval for Bayesian analysis and all sorts of other stuff, which I just think if you need to know the difference between a credible interval and a confidence interval or a predictive interval, then you're halfway through a dissertation for a PhD or something. It's just not useful for everyday decision making.
Yeah. Yeah, no, I agree. That's probably why I forgot about a lot of this stuff. I mean, I've used confidence intervals, on a regular basis. And somebody gives me a pile of data, it's a sample, and where's the actual mean going to exist? And is the average that we're producing and filling this bottle, or, the size of this loaf, is it going to fit in the packaging? What's our ability to do that? And tolerance would be between those two, I could answer vast majority of the questions that we're interested in and go with it. So most of my experience has been confidence intervals. And then on occasion, it just made more sense because we're talking about individuals. So we'll calculate a tolerance interval. But yeah, I've almost never. Now, the only time I even think about prediction intervals is when I'm doing a warranty analysis and what's next month's warranty value going to be. And I don't know that the way we actually do that is a prediction interval. I think we extrapolate the existing distribution and say, all right, well, they're a month older now, so we expect the probability of all these failures to occur times how many is still out there. And then we get a number, but I don't remember ever applying a prediction interval to those calculations.
No, I mean, again, a prediction interval can apply to a single loaf of bread as well, so to speak. So
if you were very interested in what's the likelihood that the next loaf of bread that we produce and measure will be within certain range, that would be a prediction interval.
Right.
Is that what they do when the inspectors come to see how well you're meeting the requirements? You run a prediction interval thing, and it's kind of like the dice roll. I don't even know that I've ever done that in that case either. It's like, what's the chance of us doing it?
I don't know, actually, but I mean, for all intents and purposes, if your process isn't changing from day to day, these statistics don't matter a whole lot. It's way more important, for example, to use an approach like statistical process control to firstly make sure your process is in control.
Yeah, so nice and stable, consistently making good, appropriately chewable loaves of bread, say 7.
Right. So you know that if you turn the temperature up or too high, it's going to do this. If you turn the temperature too low, it's going to do that. You know that if the fan that's inside the oven turns off, so the top loaves of bread get more heat, the bottom loaves of bread. That's what, really understanding or controlling your process is all about. Statistical process control is really good at helping you uncover scenarios where you might not be as in control as you might think. And that could be, for example, a good example is where that fan that circulates that hot air, all of a sudden there's an obstruction that you can't see. And the first thing that you notice is that the chewability of your breads start being a little bit more variable. Still within specifications perhaps, but a little bit more variable. And that's a fantastic early warning. Go, okay, this is not okay. And that might be the time where you say, we'll stop for 5 minutes, just inspect it. Oh,
there we go.
Our fans uncovered is slightly covered, and because you will never know that
come from.
Oh, sheet of plywood in a baking. All right.
Yeah. Whatever. It could be whatever.
Yeah.
But that's probably a subject for a whole nother discussion. But
absolutely.
Anyway, this is one of those questions that's like, and I think the term I picked up on as the good summary is it's semantics. There's all these different tools and techniques and methods and processes out there and stuff. Is focus on the ones that are useful and the ones that actually help you make better decisions. And, if you really need to know the difference of all these different intervals and bounds and all other stuff, enroll in a university study program and take a bunch of courses, and it'll expand your knowledge of all these things, which is great. There's no harm in that. But it's also, you see people confusing these on occasion. So being aware of it and asking these questions makes sense. So hopefully the short little description of these, and Chris, you're erudite, is that the right word? Description of these, or elucidating? No, not hallucinating. Illuminating description of this hopefully helps a few people understand some of these differences, and they can go figure out more of it in other places, or send us a question if you want to continue that discussion. So you can head over to accendoreliability.com/go/SOR, and there's a couple of ways you can get in touch with us there. The question I got that sparked this discussion was direct. It was from the About page on Ascendo. And you can also find Chris and I and the rest of the hosts on LinkedIn. So there's plenty of ways for you to get in touch with us. And so we look forward to your questions. So I'm going to take my statistics hat off and relax for the rest of the day, I think. See what happens.
Well, I'll sleep easier.
Yeah, that's true. All right. Well, thanks, Chris. Thanks for clearing that up a little bit.
Thanks, Fred. Always a pleasure.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.